All right, so this is how it appears today. So the visual appearance is a bit different than other lectures. I hope that this is technically more solid than using an iPad. iPad connection seems to be the one that is breaking and causing all kind of difficulties. I'm still able to make my drawings top of that presentation, so hopefully it will be fine. So its sound is good. How it appears? Is it like the view and everything is in a good size?
Yeah.
Good. Everything is good. So let's see if I'm able to make a record. I'm hoping two things to happen today. Two things. First thing that I was hoping to happen is that I'm able to deliver full lecture, meaning 45 minutes plus 45 minutes without any technical difficulties. And the second thing that I'm hoping even more to happen is that today is a day that we're gonna score 100% in first in-class quiz. And I'm thinking it will happen. I think it will happen because, listen to me, and you will get all the ingredients to answer correctly to first in-class quiz. And remember, before entering your answer, remember this: particles do not have rotational degrees of freedom. Keep that in your mind. Also, keep it in your mind that so far there have no discussion whatsoever regarding the moments of forces. So how is my YouTube officer? You have a complaint to make.
This screen is not showing some of the particles.
Okay, so the screen is off a bit.
Yeah, like half.
Half of it is off.
It's like this little something is not coming.
Okay, so that was the first thing. Delivering the lecture without technical difficulties. Gone. So only thing that is left is, I have all my hope to you guys. So please make it happen today. Please. Think about it carefully. So I need to go to this thing here. I need to make a little bit of settings. So I need to... All right, so that was just way too big. So I need to make it a bit smaller, like this. I'm gonna lock this again, and I'm gonna go back to my presentation. Hopefully it's better now. So it's gonna take like some 20 seconds or so, and then it's supposed to appear good. All right, good, very good. Again, remember, we haven't discussed about any forces. Why is that? Because we are discussing about the kinematics. Kinematic is an art of motion. Art of motion. And how the art of motion will take place because of the constraints. And we can have two different types of constraints. We can have like conventional constraints that are coupling tenuous coordinates together. So they are limiting the motion possibilities. And that's why the mechanism is moving in the way that it is moving. We can also have driven constraints. And those are the ones that are imposing the motion to our system. But keep in mind that they are imposing the motion. They do not impose moments of forces. So we have not discussed about moments of forces. We will do it today. Later today, we're gonna move on and we're gonna open the topic of dynamics. But so far is about kinematics. There's a clear difference between the kinematics and dynamics. Keep that in your mind. Don't get confused about that. All right, so what we will do today, we're going to wrap up the topic of kinematic analysis. And this will be one of those highlights in your life. Because we're going to solve the kinematic analysis of the system, which is not very complicated, but still, we're going to make it happen. With your skills, you can extend that knowledge and you can apply that knowledge to any mechanism you want. You just follow the certain steps and everything happens more or less automatically. All right? And then what happens is that we start the topic of dynamics, and that start with the concept of virtual displacement and virtual work. Very, very difficult concept to understand. And I'm going to make my best effort to explain what's the deal with that. And I try to give you hints, like what are the ways that helps you to understand these complicated concepts. And I'm sure that you have heard it before. This is not the first time you heard the word virtual work or virtual displacement, but often the whole concept is not so clear. So let me try to make a concrete example and concrete explanation why we need it and what is its role, what is its physical interpretation. Okay. Now, before moving on, there is something that I would like you to be aware of, and that's something that I would like you to be aware of is a MEVA seminar. MEVA is a university spin-off. It's not the recent spin-off, but is a company that was established, say, thinking like 14 years ago, and it is a company that is specialized to, high-end multi-body dynamics, high-end things to do. And one of the things that they're doing is real-time simulation. And they are making different kind of real-time simulators to different product processes. And they are having the annual seminar next week, actually. And I got the message from the MEVA, and they're hoping you to sign in. This is a meeting event that is free of charge. They offering lunch, so it's maybe even you're getting some money when you do this participation, and not just the free lunch, but you can learn things that are quite amazing. There are things that are explained by industrial companies. There are presentations that will be delivered by MEVA representatives, and I'm sure this will be an enjoyable meeting even. I mean, there are kind of like two reasons to participate. First of all, to learn state-of-the-art things, and also to get to know members of Finnish industry. That may be useful when you're looking your summer position, when you're looking your thesis position, and so on and so forth. So maybe this is something that is worth to participate. Transportation will be organized from Lappeenranta, so there will be a bus transportation that leaves early in the morning and takes you back late in the evening. So how to find out this registration website? You just need to log into website that is meva.com. So let me see if okay, like that. All right. I got the message from Jarkko that it is a good idea to explain Euler or the concept of Euler angles one more time, because it seems that there's still a little bit of confusion what comes to that one weekly assignment. It seems that that's a bit difficult because sometimes people are mixing the coordinate systems. And let me get started with this explanation by first explaining that there are two different coordinate systems. There's a left-hand coordinate system and right-hand side coordinate system. And you have to pick the one. It really depends on your preference. I think both are valid, so there is no bad or there is no good selection, but you just have to pick the one. And once you do your selection, then you have to be consistent. You cannot change that coordinate system any longer, but instead you have to stick whatever is your representation. All right? I have an example here how to solve this weekly assignment using left-hand coordinate system and right-hand coordinate system. Okay, but still, what is the most important thing about this coordinate system? That's of course our gang sign. Of course, yeah, this is a left-hand coordinate system, positive direction of rotation, respect. Okay, so you're in my gang, you're in my gang. So we have like 2 members in my gang. So not that many. All right. Anyway, so let's go on. Let's take a look. Remember there was this concept that I was hoping you to express the rotation around the y-axis, original y-axis, and amount of rotation was p divided by 6. P divided by 6. So let's take a look at this situation. Now let's get started from the left-hand coordinate system. So the left-hand coordinate system, that's where we're going to get started in the beginning. So let's take a look here. So this is how it goes. So this is X, Y, Z. And now how it is in this picture is this. Z. Oh, no, it's not this. Let me take a look at this one more time. So Z is pointing upwards, and the Y is pointing, it's like this. I'm not very flexible, so soon I'm going to have a serious difficulties here. But this is how the coordinate system is. And then I'm going to introduce a positive rotation around the Z-axis. Such the way that the rotation, or the amount of rotation is P divided by 2. That's 90 degrees. And what will happen as a consequence of that first rotation is that X-axis will take a place of original Y-axis. This is described here. So let me change the color. So I'm going to change the color of this pen. Anyways, I think it is not important this time. You can still see that this is due to the first rotation. So take a look at this. So X-axis, originally pointing this direction, is now pointing this direction. And that's because of the first rotation, which is amount of P divided by 2, 90 degrees. Okay, so now we're ready to do this rotation that was this P divided by 6. So I'm going to go ahead and take a hold of this X-axis here. I'm going to do my rotation, which is P divided by 6. And then I'm going to go ahead and take my final rotation in such the way that the first rotation is compensated. I'm rotating that in a negative direction, amount that is P divided by 6. And this is, this is my hand drawing, so it's not really perfect drawing, but this is how it looks. Now, when you compare that to original configuration, it actually appears that system is rotated around the Y-axis. Okay, same, but this time, right-hand coordinate system. I don't know why I'm a big fan of left-hand coordinate system. I know that I don't know, do we have a German team this year? We do. I know that in German it's like, is it German law that you have to use a right-hand coordinate system? Okay, so I heard that you lose your citizenship if you start using left-hand coordinate system. But maybe that's not true. Anyway, so how it goes in this time. The same procedure. We just have a little better definite set of coordinates. We have an axis that is pointing originally in a different direction. Again, first rotation is around Z-axis. And because of that, the X-axis is pointing upwards. Then I'm going to introduce my P divided by 6 rotation. And then once I'm done with that, then I'm going to go ahead and take a hold of Z-axis and introduce or compensate the first rotation with the amount that is minus P divided by 2. That's it. So that's how it goes. Hopefully it helps, this explanation. Well, let me summarize what we discussed shortly last week, and then we're going to go on. We're going to take a look at the first kinematic analysis. So we discussed about redundant constraints. This is, by the way, often that is asked in written exam. So what is a redundant constraint? Well, redundant constraint is a system that includes the constraints that are not independent, but instead they are constraining the same coordinates. They're constraining the same kind of motion. Example is a door with the 2 revolute joints on it. So here is my first revolute joint, and here is my second. They're constraining exactly same motion. They're constraining the exactly same generalized coordinates in exactly same way. So they are not independent. So they are depending on each other, and because they are depending on each other, this is what is causing redundant constraint. Redundant constraint is not a major problem because many commercial software is able to recognize redundant constraints, and they can automatically eliminate them. But the problem that remains is that the reaction forces due to the constraints will be unclear, because it is not clear how those removal or how this some of the constraints will be coming off from the picture. So that's why it is not the good modeling policy to use redundant constraints. Okay, then we moved on. Last week we already opened the topic of kinematic analysis, and we concluded that it consists of 3 steps, where the first one is the most difficult one. This is where we have to find the position coordinates, that's tenurized coordinates. Because from this on, the thing we wanted to solve, the question mark is tenurized coordinates. And what we're going to do in the position level analysis is that we are using iterative process to update our tenurized coordinates until the difference that is needed to update my coordinates is small enough. We will take a look at that. What comes as a part of that iterative process is a Jacobian matrix. Jacobian matrix will be used in dynamics as well. But here in the kinematics, it was computed in such a way that if the constraint is called vector C, then, and if the tenurized coordinates are Q, so it's a partial C, partial Q, that's what is called Jacobian matrix. C is a vector of constraints, Q is a vector of tenurized coordinates. So this gives you a matrix, and if you have a kinematically driven system, this matrix will be skewer in size, meaning that there's equally many equations than unknowns. Let's make this clear. What are the unknowns? What are the things that I'm solving here? Tenurized. How long was that? Just a few seconds. Okay, so what are the unknowns? What is that I'm solving here? These ones, tenurized coordinates. What are the solutions? What are the ingredients to make this solution to be possible? That's constraint equations. So the constraint equations, that's really what I need. Once I have a constraint equation, then I can run the kinematic analysis. All right? So now these are the other levels. So let's take a look at this position level analysis. So we concluded that this can be carried out by computing something that is called Newton difference. The Newton difference is the direction or the way the tenurized coordinate is supposed to be updated in order to reach the convergence. And this is numerics. Keep this in mind. Because, we can measure, how much we have to update the tenurized coordinates. Once this updation, this adding, will become smaller than the certain tolerance, then we can say that we reach the final destination. But if it is bigger than the certain tolerance, we have to keep on walking until we reach the final destination. So that's how it goes. So how many times we have to operate or we have to iterate the system? Well, that's a little hard to say. It depends on the application, but typically number of times. But still usually less than 10 times. The less 10 is something that is a good rule of thumb. All right, so Jacobian matrix is the one that we need in order to compute this Newton difference. And again, the Jacobian matrix is the one that consists of rows that are equal than the number of constraint equations, and columns that are equal than the number of tenurized coordinates. That's what it is. So let's take a look at the first in-class quiz. My first in-class quiz is the one that I showed to you last week. So the dimension of Jacobian matrix tells you rotation of a particle. Okay, hold on. I don't think I have a Socrative on yet. So let me put it on. So you ready now? Okay. Here, so now I'm able to log into Socrative. Teacher locking. All right, so gonna launch this one. All right, so I can see that I have already what it is, 70 students 70 students, and again, you can see the question. The question is the dimension of Jacobian matrix tells you, and choices are rotation of a particle, color of the body, number of degrees of freedom, how forces are imposed to a body. Now think about carefully what I mentioned so far. All right? If you're not, say, 100% sure, if you're not 99% sure, come here and ask what's the correct solution. I can tell you that. So you have no clue. So you're 100% sure. You sure that you're 100% sure?
Yeah.
Good. Others, you're 100% sure you know exactly what is the correct answer here. Is it like, yes, can-do attitude? We'll make it happen today. Yes? Okay? So let's wait until okay, so I've got the 50 students that already entered the answer. Maybe I'm going to wait a little while. I think that's what I'm going to do and come back to this. So let's move on. And let's look how is that I can actually do this position level iteration. So the first step to make this happen is that I have to derive the constraint equation and compute the Jacobian matrix. So those are the two ingredients that are needed to carry out the position level kinematic analysis. So again, constraint equation. Jacobian matrix is a consequence of constraint equation because that one you can get by differentiating constraint with respect to your generalized coordinates. All right, then you calculate the Newton difference, and with help of Newton difference, this is this step here, you're gonna compute the new set of generalized coordinates. You're gonna get the better guess where the solution is heading. And once you have the new set of generalized coordinates, then you need to go ahead and update the Jacobian matrix. Actually, I can see that there is one thing that is missing here. You also need to update the constraint equations because the constraint equations are a function of generalized coordinates. So you need to update that too. So let me write it here. So update, this is difficult, update C, which is constraint equation. Then you can check if, how small is this Newton difference. If it is less than a certain predefined tolerance, then you're good to go. Then you're ready to move on. And this is how you can solve the position level analysis. Now the other levels are mathematically quite involving. And that's all right because it's still mathematics. And we have tools to play with the mathematics. So no worries here, but they look ugly. They definitely look very bad. But how it goes in reality, I will explain you with one example. Velocity level analysis, how you can carry that out. Well, you have to differentiate your constraints with respect to time. We're not going to touch the details this time, but once you compute the C dot, meaning that you differentiate the constraint equation with respect to time, this is how it reads. So you're going to get as a solution, such the way that you have here Jacobian matrix, then you have here velocity of generalized coordinates, and this is a vector you can get by differentiating the constraint with respect to time. Where this is actually coming from, it is coming from the chain rule of differentiation. Now, this is the one you can solve here, and once you solve it, this is how you can solve the velocities of generalized coordinates. Again, ingredients you needed here is a Jacobian matrix. Now look at this again. Again, you have to invert the Jacobian matrix. Only way to make that happen is that you have to have a skew Jacobian matrix. Otherwise, it's not mathematically possible to do so. Acceleration level is a major headache. It's like a nightmare, but that's all right. what you can do is that you can simply differentiate your velocity level expression, which is this one here, one more time with respect to time. And what you're going to get as a result is that you have here Jacobian matrix, which is multiplied by acceleration of tenderized coordinates, and that's exactly what you're going to solve out of this equation. Then you have here constraint equations that are differentiated twice with respect to time. And believe me, you have no idea, like, what the heck is this? Like, times differentiated twice with respect to time. No worries, because the example will tell everything for you. And then there I have here a monster component, which is a Jacobian matrix multiplied by velocity, and that solution is then differentiated with respect to tenderized coordinates. Very bad. Let me repeat it. So it's a Jacobian matrix multiplied by velocity of tenderized coordinates. That's going to give you a vector. That vector is one more time differentiated with respect to tenderized coordinates. And then this is that differentiation. And the solution is finally multiplied by velocity of tenderized coordinates. It's quite involved. But again, symbolic math tool will make it happen for us. And then I have here the final component, which is a Jacobian matrix that is differentiated with respect to time, and that is then multiplied by velocity of tenderized coordinates. That's how you can finally get the acceleration. It looks bad, but it's all about the substitution. You substitute your information to this equation, and then you're going to get it. Okay. So here's a summary. Position level, you need to get the Newton difference. So it's about the iterative process. Velocity level, substitution. Acceleration level, substitution. You got it. Can you do me this? Are you depressed? You shouldn't, because this is still soft, very soft, when comparing that concept of virtual work. That's difficult. You comfortable? So now let's take a look at an example. I have here not very complicated system, but this is a system which consists of one moving body. Let's take a look at that, but before that, let's see if today is a day. How is the success rate? Above 90? But is it going to be 100% or not? 96. Who is saying 100%? It's just you and me. You don't even believe this by yourself. Think about it, Think about what I just was explaining about rotation of a particle. It's like a Santa Claus. It's a myth. It's not possible to have it. Then, color of the body makes no sense. Makes no sense. Color of the body. We haven't discussed about anything about the color. And then forces. Remember, nothing about the forces. Only thing that is left is C. So it was. Okay. So, but I have good news. Good news is this. 81%. 81%. But remember, particles do not have this rotational decrease of freedom. That's what I'm desperately hoping you to remember out of this course. Please. And then forces, again, no discussion about the forces whatsoever so far. Okay, but, I still have, let me think, 2 more in-class quizzes to come. So it's still possible because, I think, this was, you were nervous and everything. Now you have the full speed. So the next time it's going to be 100%. Okay? Because what we need is, what is the key for success in this course? Can-do attitude, correct. Can-do attitude, that's the most important thing. All right, so we are going to this example. Okay, I have a mechanism that consists of one moving body. And this mechanism is constrained by primitive joints, 2 of them. First primitive joint is located in a position P, which is this one here. Another one is located in a position Q, which is another end of that beam-like body. You know how to constrain this system already. So you can make this, you can express these primitive constraints using the kinematics that we are very much familiar with. And the kinematics that we are very much familiar with, let me repeat that one more time. So that's R, which is a translation of body reference coordinate system, plus orientation of body reference coordinate system multiplied by vector u bar. So we're going to use this equation to express these primitive joints. Then I have here one additional constraint. And one additional constraint is that, you know, here in a point Q, it is this motion along the global x-axis is originally left to be free. But now I say that actually this is no longer free, but instead this one has to follow the certain rule. And the rule is expressed here. This one has to follow the equation that is stated as a sine, which is a function of time, divided by 4 minus 1 divided by 2. So that's my constraint. And this is a driven constraint. How this is driven constraint? Because if you're going to make a graph, how is it moving? So if I'm going to make not x but time, and this is this function, let's say constraint, it's going to be like this. So it's moving back and forth. I'm forcing it to move back and forth. All right, so what do you think? Can we solve this? Of course, because of can-do attitude. So let's make it, and not just that, but we have the knowledge to do it. You know, if you don't have can-do attitude, but you're not following the course, it's not going to help you to solve this problem. But we have both. So let's first compute the Jacobian matrix. So this is the step number 1. So we need that. What are the ingredients? What are the components that we need in order to compute the Jacobian matrix? Well, we have to know what is a vector of generalized coordinates. How many components we have in a vector of generalized coordinates? In a body, in this system. In this system. Okay, so how many generalized coordinates we have in this system? 3. Because everybody needs 3. Everybody needs 3. What are these 3 coordinates? Well, they are translation of body reference coordinate system, that's 2 coordinates, and rotation of body reference coordinates. Okay, so we have 3. So we have 3 unknowns. How many equations we need to solve these 3 unknowns? 3. How can we kind of get it? Well, by introducing the constraints. So we have 2 primitive joints plus 1 driven joint. That's 2 plus 1 equal to 3. So things are matching. So it's possible to make it happen. All right, so let's get started. Let's take a look at this point Q, where I have 2 constraints that I impose to this system. 2 constraints. First thing that I need to do is that I have to express this point with respect to my global coordinate system using the kinematics that I'm using over and over and over again. Okay, so I'm going to get started here. So this is where I'm starting. So I'm going to first travel the origin of body reference coordinate system. That will be possible with help of vector R. Vector R in 2-dimensional space consists of 2 components that are projection in X and projection in Y coordinate axis, global coordinate axis. All right? Then I have to account the orientation of the body. That's going to be carried out with help of 2x2 rotation matrix, which is a function of angle theta. All right? So this is how it looks. So now I'm here in my body reference coordinate system, and I need to use a U-bar to move from this location to this location. How can I make it happen? So it's going to be here such the way that if the length of the body is L, so I have to travel here L divided by 2, and then the Y direction have to be equal to 0. Now what these coordinates have to be? Let's get started from the X coordinate. So the X coordinate is the one that have to follow this driven constraint the one that is imposing the motion. So this part, which is x, well, equal the global x coordinate axis, have to be equal than my driven constraint. Y coordinate, which is a motion in this direction, have to be equal to 0, because motion in that direction is not allowed. Not allowed. Okay, so that's when I substitute that information. So it was a minus, well, let me take a look at here. Minus L divided by 2 and 0 gives me two constraint equations. So this is how they read. So those are the two constraint equations. One more to go. One more that is associated to this point here. So any ideas how to make it happen? By repeating. Repeating, repeating, repeating. No thinking. No thinking. This is the beauty of multi-body dynamics. Absolutely no thinking. Okay, so we're going to take this equation again. So first we're going to travel to body reference coordinate system. We're going to account its orientation. And with help of vector u bar, we end up to be in a point P. And then we set the constraints. How are we going to set the constraints? Well, the motion in a x-axis, this axis have to be equal to 0. Beautiful. Beautiful. So that's how it goes. So let's set it. So these are the ingredients that I needed. This is going to be my third constraint equation. What I'm going to do next, I'm going to use a bunch of symbolic math to compute my Jacobian matrix. Now the equations are not visible here, but let's take an example of the third constraint equation. This one. I'm going to first differentiate this third constraint equation with respect to Rx. That's going to be equal to 1. All right. Then I'm going to differentiate that equation with respect to Ry. That will be equal to 0, because Ry is not mentioned in this equation. All right. Then I'm going to take this equation one more time and differentiate that with respect to angle theta. It's going to give me minus L divided by 2 in cosine theta, because of how I differentiate the trigonometric function. The similar way I compute the others. So it's very, very mechanical. A little bit of mathematics, but very mechanical mathematics. Mechanical mathematics, that's by the way, a nice word, I think. Because we're in a department of mechanical engineering. Okay, so anyways. So that's how it goes. So this, how we finally can solve the Newton difference. It's not the solution, but it's the way we can find the solution. By keep on updating these coordinates, we are able to find the final destination. So it's giving me the direction where to travel, how to update my coordinates, and once I do so, I'm getting closer and closer to my final destination. Once my location is close enough, under the tolerance, then I can stop. I don't need to search anymore. So this is how I can do this position level analysis. Clear? What about velocity level? A little bit painful, but doable. Look at the ingredients we need here. We have almost everything here, because we have here the Jacobian matrix. That's the one that we have to invert. And then we have to have one more thing, which is a constraint equation differentiated with respect to time. All right. Sounds bad, but it's not, because when you look at the constraint equations that are located here in the upper right corner of the slide, there is only one constraint, which is a function of time. And what is that? Yeah, correct. That's the driven constraint. That's the one that is introducing the motion to my system. Others are not function of time, so when I differentiate that with respect to time, they will disappear. Okay, so I'm going to take this one here, differentiate that with respect to time. So the only thing that is where the time is mentioned is, this one here. So it's going to be minus 1 divided by 4 multiplied by cosine time. Clear? That's it. So this is my velocity level analysis. Again, look at this. So it's not about iterative process, but it's just substituting the information there, and magic equation gives me velocity. Acceleration analysis, the same thing, bit more involving, but other than that, is very mechanical. First thing that I need here is a Jacobian matrix. We don't need to discuss about that. That's already clear-cut case. But we need constraint differentiated twice with respect to time. So we need to take one more step from that previous step and differentiate the constraint twice with respect to time. And then that painful component. We just have to do it. Nothing helps. But let's make it happen. So let's take first, and this is that painful component. So let's first take the Jacobian matrix, which is mentioned here. Now let's multiply that with the velocity of generalized coordinates. Well, it's a matrix multiplied by a vector. Well, we know how to make it happen. It's not too difficult. Let's just do it. And once we do it, we get the vector of 3 components, and this is how the 3 components reads. Now we're going to go ahead and differentiate these 3 components with respect to generalized coordinates. We're almost there. So we're going to do this. This is how these 3 components look like. And now when I differentiate those with respect to generalized coordinates, this is how it looks. Again, we are not paying too much attention about the mathematical details. And why is that? Because they're mathematical details. And we wanted to learn the big picture. Okay. Now once I got these results, and I'm going to differentiate, multiply that one more time with the velocity of generalized coordinates. Now this is the component that I needed in my solution. This is the component that I'm differentiating twice with respect to time. That's going to be reading like that. And this is going to be equal to 0 because the Jacobian matrix is not a function of time. Okay, so you're ready. Okay, next what will happen is mind-blowing. Seriously, because I already introduced these equations to MATLAB. We're going to solve these kinematics. So are you guys ready? Breathe deep. Take a good hold of your seat because it's going to be really magnificent. I'm not going to take a look at this equation, but instead I'm going to move on to my MATLAB. MATLAB is here. We can take a look at these examples later, or this implementation later. Are you crying? Because you should. Look what happened. Look, you realize what just happened. It looked that there is a bar moving like this. Yes, there was a bar moving like this, but there was a bigger story behind, much bigger story. What is this bigger story? That now, with your knowledge, you can solve the kinematics. Let me summarize. And now I have here angular acceleration, that's what I'm plotting out, angular velocity, orientation of local coordinate system and or x position, so on and so forth. I can plot all this information. Beautiful. Absolutely beautiful. Isn't it? But you're not crying. Okay, but let's look at the big picture again. So again, I'm gonna put these MATLAB files to Moodle side, so you could take a look at them if you want. But let's look at the big picture again. So we were following the certain step. Number 1, create the Jacobian matrix. You can make it happen, so you can do it. Number 2, Newton difference for position analysis. You can make that happen too. Number 3, velocity analysis. Number 4, acceleration analysis. Done. And here is exactly how the multi-body system dynamics goes. You're just following the 4 steps as explained in these previous slides, and automatically you get everything you need in order to carry out the kinematic analysis.
Three-dimensional space it becomes more complicated.
Well, the difference in a 3-dimensional space and 2-dimensional space is that then the rotation matrix will be a little bit painful. This is in a kinematic analysis, not the serious problem. It's not the serious problem in the dynamics. It becomes to be, well, a headache, at least, if nothing else. And why is that? Shortly, I can explain you why. And I can guarantee you this. There's 100% certainty that what I'm going to explain you, you will not understand. Still, I'm going to explain it to you. Okay? So what's the deal in a 3-dimensional space? You know, in a 3-dimensional space, angular velocity consists of 3 components. All right? So angular velocity consists of 3 components. This is supposed to be omega. You know, excuse my writing. So omega, which is angular velocity, consists of 3 components. Those could be associated to body reference coordinate system or global coordinate system. Either way, it doesn't make much difference. But this is a vector that consists of, you know, omega x, omega y, omega x, which is angular velocities with respect to 3 different coordinate axes. Then, vector of generalized coordinates are associated to rotations. This could be the one that we looked for based on the earlier angles. I think we used the notation, let me think, it was what the heck is the name of this? Doesn't make any difference, phi. But anyways, it's phi, and then theta, and another thing that I don't know. But anyways, this too is 3 coordinates like this. And now when the difference that this with respect to time, they are not equal the angular velocity vector. They are not. This is a source of difficulty. This is where all the problem becomes. And, you know, they are, you know, it's a long story, but no worries because we are not going to take a look at that in details in this course. But again, you want to be my doctoral student, oh my God, your life will be all about this and more complicated stuff. Okay? Do you want to be my doctoral student? Hell no. Okay, so what do you guys say? Should we have a break? Let's have a break and let's take a look at another example and then more in-class quizzes, and really there's something that you need to go and get some coffee because we're going to start discussing about forces. There is an introduction that you have to watch. You have to pay a full attention because if you don't get my introduction, rest of the course you will be off. Okay? What is that? Oh, yeah. Yeah, by the way, the one thing that I forget, because I got the feedback from online participants that I need to repeat the questions, and I forget it already. So if there is a question from the audience, it is important me to repeat it because they don't hear you, which is very good because you are not appearing in a YouTube. Like if you're asking something, audience, online participants cannot hear you. All right, take it easy and come back. Oh, what I say, like 10 minutes. Is it 10 minutes all right? 10 minutes.